Okay, welcome back. I am Mark CDT, Theory and Simulation course. We continue today with the relaxation theory. Specifically, what we'll be looking at is the things that we have left unexplored in the previous lecture when we derived practical theory. That is the correlation functions. All of you probably came across relaxation by now in your magnetic resonance research. And all of you have heard about correlation time and correlation functions and the spectral density functions that occur in the expressions for the dipolar relaxation rates, the CSA relaxation rates, and other such things. What we'll do today is find out where they are coming from in a fairly rigorous way. Most textbooks hand wave through the argument, but it's fairly important, and it becomes essential by the time your motion is complex to actually understand where they're coming from, and we'll do just that today. We did establish in our rotations lecture that our Hamiltonian has the following general form in the case where it is rotationally modulated. We had a sum over k and m from -2 to 2. We had our second rank Wigner functions, k, m, and they depended on time, or more specifically, they depended on the angles that molecular orientations are specified by, and the angles themselves depended on time, and so we just write it in short as Wigner functions depending on time. And then our rotational basis, all those 25 operators. So this is the time dependence of the anisotropic part of the Hamiltonian in the case of the rotationally modulated interactions. And then these functions, we called them Q in the relaxation theory lecture, because we wanted to be general there, and this is just specific to the rotational case. They had the correlation function. And we'll define the correlation function between two Wigner functions. It will have to depend on 4 indices, therefore. So it will be GKMPQ of time tau as the correlation function between D to Km of time t, and then D to star PQ of time t plus tau. And we also noted that for stationary random processes, the correlation functions, just as all statistical properties, do not depend on the time offset t, they only depend on the time difference between the processes we are correlating. And so we could translate the entire sequence to the origin, and so this was d2km of 0, and then d2 star pq of tau. And that was the correlation function. The angle brackets here denote ensemble average. What I will do now is change perspective in a way. Instead of looking at an individual system, how it moves and tumbles, what I will be looking is at distribution functions in an ensemble of systems. So for example, if we are looking at an average value of some variable x in an ensemble, what we can define it as is an integral from -infinity to infinity x dx dx, which is just a generalization of the average, yeah, where x is our variable and px is the probability density of that variable. In the discrete case, it would have been the different values of x multiplied by the corresponding probabilities, summed over. And so, because the average is an integral of the value times the probability, we can recast this average in the same way. We can take integrals over the probability distributions in the system. Now, in this case, we only have one variable, and so we've got one probability distribution. In this case, we've got two. We've got the Wigner function at time 0 and the Wigner function at time tau, and so it will be a bit more complicated, but not much more so. So when we recast it in terms of probabilities, what we are going to get is the following. There will be a double integral, because we've got two functions and two distributions to look at, then d to km of omega 0, that is the angles at time 0, and the Wigner function of that angles, then d2 star pq of omega, which is the angles at time tau. And then, just like we had here, so this plays the role of x, and we now need the probabilities. The first probability that we need is the probability of a system having been at the angle omega 0 at time 0. We'll call it just p of omega 0. And the second probability is a bit more subtle. It's the probability of a system turning up with angle omega at time tau, having been at an angle omega 0 at time 0, which is denoted like that. So omega tau subject to omega 0 at time 0. And now we need to integrate this distribution over all the variables we have, and that means d omega 0, where this could be Euler angles, it could be some other parameterization of the rotation group. Now it's a bit of a complicated equation, but it becomes conceptually easier to understand if we treat these probabilities as chemists do. So when a chemist looks at a distribution of molecules in some liquid sample, he can call that a probability distribution, but more commonly it's just called concentration. And so these probabilities are much easier to understand if they are interpreted as concentrations of systems in some angled space, much like we had concentrations of molecules in just a three-dimensional Cartesian space in here. And in that case, these integrals, they're just recast in an understandable form as averages across the sample. So they're easier to understand if we look at them as at concentrations. And one other intuitive thing that it becomes immediately clear if we treat them as concentrations is that they should obey the diffusion equation, as all concentrations do in a liquid sample. Okay, so at the moment we know nothing about this, how it depends on time, and we can assume a few things, but we don't really know much about this either, and so we need to take a more careful look at what these things are before we start treating them. So the first assumptions, they start from here. So from now on, we will assume that our molecules are spherical particles and that they are undergoing isotropic rotation or diffusion. And more specifically, we will assume that we are looking at an equilibrated sample. Now, in an equilibrated sample of spherical molecules, all orientations at our initial time 0 are equally probable. And so this p is just a constant, which is the same for every omega 0. And in order to make it integrate to 1 when we integrate over all three Euler angles, what we need to put it to is 1 over 8 pi squared, the full body angle. So that's a constant, and our integral simplifies, well, just a tiny little bit. So we'll just rewrite it in here, so 1 over 8 pi squared, double integral d to m of omega 0, d2 star pq of omega, and then this probability, system being at omega at time tau, having been at omega 0 at time 0, d omega 0 d omega. Okay, well, Wigner functions we are fairly comfortable with. What we don't really know much about at this point is this probability. What we do know, however, about it is that it is a kind of concentration, except it is a concentration in the angle space. So we can put it not as a concentration in this sample, but as a concentration of systems on a surface of a sphere. So two angles, alpha and beta, will determine the direction of the point on a sphere, and then the angle gamma is the rotation around that beta. And so we will have diffusion, but it will be a diffusion of a rotational type on the surface of a sphere. So the second assumption that we are going to make is that our system obeys the isotropic rotational diffusion equation in the three-angle space. And that we can simply, well, we could have derived it, but it's a bit of a long story, we don't have the time. So we just look it up in a textbook, and the textbook says d by d tau p of omega and tau, having been at omega naught at time 0, is minus d, the rotational diffusion constant, and then Lx squared plus Ly squared plus Lz squared, where Lx, Ly, and Lz are the angular momentum operators. Yeah? Lz was x d by dy minus y d by dx. We derived them a few lectures ago, times p of omega tau, omega naught, 0. Now, I'm skipping the derivation of this, but it can be obtained fairly simply from one very fundamental observation. I think I mentioned it already, and we did derive in the rotations lecture the fact that Lx is the infinitesimal generator of the rotation around x, similarly for y and z. And the fundamental theorem states that if Lx is a generator of a motion, then Lx squared is the generator of diffusion process along the same chord. And so if we're looking at independent diffusion along the three possible rotation directions, that would be just the sum of squares. So that's a kind of hand-waving argument for where this equation is coming from. And if you require the rigorous derivation, just look it up in Landau-Lifshitz. Right, so what we need to do now is to solve this standard variable separation procedure. And what we do know about this operator is this is L squared, yes, the total momentum. And we know what the eigenfunctions are of the total momentum, the Wigner functions. And so it is reasonable, therefore, to solve this equation in terms of linear combinations of Wigner functions, because they will transform in a particularly simple way under the action of our operator here. And so I'll do the variable separation now. I will split our P here into a sum of products of pure functions of time and pure functions of space. And that is the general expression for the general solution for such equations. So noting here in brackets that we know the following fact. So L squared, this is Lx, Ly, and Lz, acting on d, L, n returns to us L plus 1 d L. And so the Wigners are the eigenfunctions of L squared, and seeking solution in terms of the following sum. So our P omega tau omega naught would be a sum over L from 0 to infinity, all ranks of these Wigner functions, then the sum over k and m from minus L to L, so all the projections of those ranks, then some constants, or not so constants, they have to depend on time rather than space, so for space they're constants, but for time they're not, km, so it's a function of tau, but also of our initial conditions, so omega naught L naught, times the Wigner function L km of omega. And this is the form in which we will look at the solution. So the standard things that we now need to do to continue solving this equation is to substitute this into the left-hand side here, into the right-hand side here, at which point the equation would split into the time part and the space part. We will solve them separately and then put them back together again. So here's our equation, here's our ansatz. Let's stick one into the other and see what happens. So putting it into there, just shifting the derivatives through the sums immediately. So L0 to infinity, sum k and minus L to L, this should be L here. Then d by d tau a L km of tau, omega naught naught, and then the Wigner functions do not depend on time, only on omega. So that is the left-hand side of that equation, and the right-hand side would be sum L0 to infinity, sum k minus L to L. The operator here would not act on A because it doesn't depend on omega, so it's A L K M of tau and the initial condition, and then minus d L squared acting on d L K M of omega. Okay, so here it is D that is not affected by the operator, and here it is A that's not affected by the operator, and what we should do now is just act with L squared on D, and what we'll get in here is L plus 1. Now, Wigner functions are orthogonal, and so we can just multiply this equation on either side by a Wigner function. It should also be L, by the way, of a particular kind. So let's just say we have it multiplied by L prime, K prime, L prime, and integrated over. And then the orthogonality would mean that all terms would vanish except for the terms where L is equal to L prime, K to K prime, M to M prime. In other words, what that means is that if this equation holds for a family of orthogonal functions, it does hold for the coefficients of those functions individually. And so what we then get out of this is individual equations that would be a system over all L, K, and M of the following type: d by d tau, A, L, K, M of tau omega naught 0 must be equal to this thing where only one term survived, that is minus d L plus 1, A, L, K, M of tau omega naught 0. Now, this is a very large system. There are quite a few of such equations, but they're thankfully independent. And we actually know how to solve these things because this is just a first order ordinary differential equation. It's simply solved in matrix exponentials. So we know exactly what this is. And so once we write that thing, what we get is A, L, K, M of tau omega naught 0. I'm just dragging this initial condition. We'll make use of it shortly. Is E minus d L plus 1. Then tau, so a decaying exponential, times A L K M of 0. Yep, some initial condition. So the time part of our equation turns out to be a family of decaying exponentials. And now the general solution to this, I will rename these A's into C's, just to emphasize the fact that they are constants of some kind. The general solution would be like this, a sum of these with some coefficients times the Wigner functions. So let's put them together, and that's our general solution, to which we have not yet applied the initial condition, and so it does contain some flexibility in terms of those coefficients. 0 would be sum L0 to infinity, a sum K and from minus L to L, and then C, L, K, M. So these are just those. I call them C's. Then D, L, K, M of omega, E minus D, L L plus 1 tau. So it became a little bit better. We now know what Wegeners are, we know what the exponentials are, but we still don't know what those coefficients are. And here's where the initial condition comes into play. We state that because of this condition, so we are looking at the probability distribution of specifically the systems that had pointed at omega 0 at time 0, that this at tau equals 0 must be equal to delta function with respect to omega 0, if they're all sticking at omega 0. And so our initial condition, therefore, when we put tau to 0 here, is the following. A sum L0 to infinity, a sum k and m from minus L to L, C L k m d L k m of omega must be equal to delta of omega minus omega 0. So all the systems pointing at omega 0. So from here we can actually extract the C's. What we need to do is just multiply both sides of this equation by some d L prime, k prime, m prime, and take advantage of the orthogonality condition for the Wigner functions. I've given it to you in equation 11. So if we multiply those Wigner functions into one another with suitable coefficients, we get the delta functions, and the coefficients are listed in equation 11. So after we apply that, we get the expression for C's. So C, L, K, M are finally equal, and this is where all the variability disappears. We now have an actual initial condition implemented, that is 2L plus 1 divided by 8pi squared d L conjugate k m of omega. And so finally what we can do is put these coefficients along with the Wigners and the exponentials into here, and that will give us the expression for the time dependence of this probability density. And finally, what we'll need to do is take this probability density, stick it into that integral that it originally came out of, and finally evaluate that integral, because we can now do it, because we know all the various transformations that Wigner functions undergo under those integration operations. Okay, this is our solution for the rotational diffusion equation that we just obtained. One last thing that I should mention that we will be using when we take that integral is the orthogonality condition for the Wigner functions. This is something that we don't have time to derive. It comes out of textbook, but we will be using it a lot. So an integral of two Wigner functions, L1, M1, K1, star, so complex conjugate in here, times a Wigner function L2, M2, K2 of the same argument, omega, integrated over d omega is equal to the following: 8 pi over 2L1 plus 1, delta L1, L2, delta M1, M2, delta K1, K2. In other words, they are orthogonal with respect to all three indices. So if any pair of indices doesn't match, we get a 0. If they do match, we do get this 8 pi squared over 2L plus 1 number. Okay, so with that in mind, let us take our original integral for the correlation functions. So our G, A, B, C, D, and I'll be using A, B, C, D here so as to not confuse things with Km that we've been using throughout the previous calculations of tau, which was defined, if you remember, as D2AB of omega 0, then d2 star cd of tau, and which we had expanded in the integral of 1 over 8 pi squared, double integral d to ab of omega naught, then d2 cd star of omega, and there was the probability density, which we can now actually plug into there. So I'll just write the probability density for now, and we'll stick it in the next line. Not d omega naught. Okay, so we now have this rather large sum, and we've got this double integral. So I'll take sum out of the integral just for convenience and collect everything that's integrable out in that integral and pull all the constants out. And so the result will be the following: 1 over 8 pi squared, sum L0 to infinity. Underneath this, everything that depends on L. So 2L plus 1 over 8 pi squared, then E minus DL L plus 1 tau, then a sum K and M from minus L to L, and now the double integral d to AB. You can see why I've chosen A, B, C, D, because K, L are already taken, of omega 0, then d2 star CD of omega, then d L star K M of omega naught, and then d L K M omega d omega naught d omega. A fairly big integral, but you can see that it splits into two independent integrals, because one pair of functions only depends on omega naught, the other pair of functions only depends on omega, and so a double integral is in fact a product of single integrals in this case. And once we write those single integrals, we'll notice that they've got exactly the form that we got for the orthogonality condition, and so we can replace them with that answer there. And it contains a massive bunch of delta functions, and so quite a few things, as you'll see in a moment, will cancel and collapse and disappear. And despite this enormous amount of mathematics that we've gone through, the final answer is actually quite simple. So let's partition those integrals. So what we get here is 1 over 8 pi squared, sum L0 to infinity, so all the usual blah blah blah, pi squared, E minus d L plus 1 tau, then another sum, K and M minus L to L. And now let's partition the integrals. So there will be the first integral over omega 0, so it will be d2 AB 0, then d L K M conjugate of omega 0, d omega 0, and then the second integral over omega, so d 2 star CD of omega, then d L K M of omega d omega. Right, so the next step, let's plug in these deltas with all the matching indices. So then what we get is this enormous crocodile. I won't copy it, it remains the same. It's in your handout, times this one here, so 8 pi squared over 2L plus 1, so I'm copying this thing here, delta L2, so L can only be equal to 2, then delta Ka, so K has to be equal to A, delta MB, that's the first one, and then we get 8 pi squared
2L plus 1, again delta L2, so these two are just doing the same thing, delta Kc, and then delta Md. Okay, and after we've matched all the indices and destroyed the corresponding sums in here, and put all the L's to 2, because the deltas here demand that to be the case, a lot of simplification later. See your handout, it's all done in there. We get a tiny equation, delta AC, delta BD divided by 5 exponential minus 6d tau. Nice and simple. So the correlation functions that we've got, the original one here between the Wigner functions, is just an exponential. Now, it acquires a familiar shape if we actually plug in the expression for D from hydrodynamics. Now, D is rotational diffusion constant. It's related to molecular radius, solvent viscosity, and other things. The Stokes-Einstein equation. So, just picking it up from the textbook, D is Kt over 8 pi eta r cubed, where r is the molecular radius, eta is the solvent viscosity, K is Boltzmann constant, and T is temperature. And the other replacement that we need to make is what people often define, is they define 1 over 6d as tau c, known in the trade as the correlation time. And so once we make all those replacements, what we get is the following. We get our G, A, B, C, D of tau becomes delta AC, delta B, D over 5, E minus tau over tau C, where tau C is 4 pi eta r cubed divided by 3 kT. That's it. So this tau C, the correlation time, is just the characteristic time of the decay of this correlation function, defined like this through viscosity, molecular radius, or well, molecular volume in fact. It goes linearly with the volume because volume goes as r cubed, and temperature. Now clearly, the greater the temperature, the faster the motion, and therefore the slower the correlation time. The smaller the correlation time, the greater the viscosity, the slower the motion, then the longer the correlation time. So it all makes physical sense. And well, here's the unexpectedly simple answer for what is a fairly complicated derivation. And this completes, at least for isotropic liquids, the Bloch-Redfield-Langston's relaxation theory, because we can now plug those functions into the Redfield integral, and it becomes possible to take, and from there all the relaxation rates, dipolar, quadrupolar, Oberhauser effects, and such like, acquire the actual values that can be compared to the experiment. And to the credit of the theory, the predicted values usually agree with the experimental values within the range of validity to about 10 to 20% accuracy. So it's doing actually quite well. Okay, so what we've just derived was the isotropic rotational diffusion, which is appropriate for a perfectly spherical molecule. Now, there's no such thing as a perfectly spherical molecule. Most of them would deviate in one way or another from a perfect sphere. And so the next reasonable question that we need to ask is what happens if the diffusion of the molecule is, for example, axial, or if in fact there are 3 different rotational diffusion constants in some 3 different coordinate directions. The question has an answer, and let's consider first the situation where the diffusion is axial. So the molecule behaves like a symmetric ellipsoid atop, and it has 2 diffusion constants. One is for the diffusion around the long axis, and the other for the diffusion perpendicular to the long axis, and so we would have 2 diffusion constants.
In that case, and again I'll send you to the textbook in this case because we don't have the time to derive such things properly, and it's not spin dynamics after all. The rotational diffusion equation for our probability distribution would be modified. In particular, what we are going to have is not just one diffusion constant, but two. One for our long axis and another for the direction perpendicular to it. So it will be minus d parallel Lz squared, so that's the diffusion constant around the z-axis, plus d perpendicular of Lx squared plus Ly squared. And that would be applied to this probability density tau omega naught 0. Now the good thing about this equation is that the Wigner functions are still the eigenfunctions of this operator, but with different eigenvalues. You can establish it by direct inspection, but the following is true. D parallel Lz squared plus d perpendicular Lx squared plus Ly squared applied to d Lkm of Wigner function. What we can do to get that is, let's just add and subtract a little bit of d perpendicular Lz to that to try and partition this into L squared, for which we know this relationship, and Lz, for which we also know it, because the Wigner functions are also eigenfunctions of Lz, because they are related to spherical harmonics. So that sort of partitioning yields the following. We'll get minus d parallel minus d perpendicular Lz squared plus d perpendicular Lx squared plus Ly squared plus Lz squared. So now we've got the L squared in here and just the Lz in there, and so we can actually act on a Wigner function now. So d Lkm of omega, and that returns us the following eigenvalue. It will be minus. So when we act with this is just LL plus 1 times d perpendicular, and this would be k squared or m squared, depending on which way around our alpha and gamma rotations go in the selection of Euler angles. So I've chosen k to be the index that's affected by Lz, but that's largely a matter of convention. So we will have L plus 1 d perpendicular, this term here, plus k squared d parallel minus d perpendicular, and then the original function Lkm of omega. So Wigners are still eigenfunctions of this axial diffusion operator, but with different eigenvalues. Now, if you remember, in the case where we just had the isotropic diffusion, we only had this term. This was LL plus 1d. And this is what ended up in our exponential in the end. So now what we've got is not one correlation time in the end, but several. So all the subsequent treatment, all this big pile of mathematics flows through completely identically, except for different indices in the exponentials. And so in the end, we get the following for our correlation function. We get G, A, B, C, D of tau is the same pile of deltas, delta AC, delta B, D, divided by the same 5, but we have the following index in the exponential: 6d perpendicular plus a squared d parallel minus d perpendicular, and that's times tau. So whereas the isotropic rotational correlation function did not depend on these indices, it was either 0 or it was the same exponential. In the case of an isotropic one, there is this dependence on one of the indices there. And we simply have, in this case, two rotational correlation times. One corresponds to d parallel and the other corresponds to d perpendicular. And they are just defined in the same sort of way. So d parallel is kt over
8 pi eta r cubed parallel. So the radius around the z-axis and d perpendicular is similarly defined as kt over 8 pi eta r cubed perpendicular. Now, because we've got a squared in here, and a goes from -2 to 2, there are 3 distinct correlation times. So the one corresponding to a equals 2 or -2, another one corresponding to a equals plus or -1, and the third one simply corresponding to 1 over 6d perpendicular. And so whereas in the case of isotropic rotational diffusion we had to solve for 1 correlation time, in the case of axial diffusion we need to solve for 3 correlation times, which are under the bonnet dependent on just 2 radii of the ellipsoid that we are approximating the molecule with for the purposes of describing its rotation. The final situation that we need to look at is when the rotational diffusion is completely anisotropic. That is, not that we've got equal coefficients in front of Lx and Ly, but we actually have 3 different coefficients for x, so y, and the z. And so our diffusion equation will just be d by d tau p with the following diffusion operator. It will be minus dxx Lx squared plus dyy Ly squared plus dzzz Lz squared times p. And the eagle-eyed would notice that I'm carefully choosing the rotational diffusion tensor to be in its eigenframe, so diagonal. It's always possible to choose such a coordinate system, that this should be the case. But the problem with this equation is that Wigner functions are no longer the eigenfunctions of the operator, where in general the 3 coefficients here could be different. Thankfully, their simple linear combinations still are eigenfunctions, and that is taken advantage of in your handout. In equation 21, it is elaborated what relationships relate the Wigner functions to the eigenfunctions of this more general case. And you've got this big table of eigenvalues and the corresponding eigenfunctions, which I've just crunched through by brute force in Mathematica to obtain the final coefficients and expressions. So what we eventually get after an absolutely mind-boggling amount of mathematics that is nonetheless still reproduced in your handout is the following expression: G, A, B, C, D of tau now contains a sum k from 1 to 5 delta B, D, so some things still remain orthogonal, and then A, K, A star, K, C. So these A's are different from the A's which are indices, divided by 5 E minus lambda K tau. So we now have 5 different decay rates, so 5 different correlation times, and these coefficients are tabulated in the handout for you. They're fairly complicated. Those who seek to just get this out of the box, all of this is implemented in Spinach. There is a function in there called correlation underscore function, which is either a single correlation time, or 3 correlation times, or 5 correlation times, or these rotational diffusion parameters, and simply spits out this correlation function as a function of tau. And the function, importantly, has been checked with Monte Carlo, so there's a reasonable guarantee that all of this mathematics has been carried through and implemented correctly in there, because the answers do match the Monte Carlo simulations for the similar things. Okay, what's left for us to do now is to put the expressions we just derived for correlation functions into Redfield theory and take a look at how they fit. Let's say we are looking to calculate a matrix element of the relaxation superoperator from a state rho A through our
relaxation superoperator into a state rho b. And I'll just copy the integral from the previous lecture in Hilbert space. It will be a sum over k m p q, integral from 0 to infinity g k m p q of tau, then a trace, which is a scalar product in Hilbert space, rho a, Hermitian conjugate, then q k m, one of our rotation basis operators, commutator with e plus I h naught tau, where h naught was our static Hamiltonian, then q p q, Hermitian conjugate, then e minus I h naught tau, commutator with rho b, then closing the commutators, then the trace and d tau. Now I will not drag you through all this multi-index mathematics on board. It's given in the handout. The bottom line is that after quite a few mathematical transformations are applied, this integral transforms into a bunch of Fourier transforms of this correlation function. You can sort of glean it. Rho A is a vector or a matrix in this case, it's Hilbert space, but it's a constant matrix. It's something that we got out of here. QKM is also a constant matrix. This, in the case where H naught is diagonal, we can always make it that way, is a bunch of exponentials, complex exponentials that depend on time. This is a constant, that's another bunch of complex exponentials, and that's another constant. So what we have is a function multiplied by some kind of complex exponential and integrated from 0 to infinity. Clearly a Fourier transform. And in this case, it's just a superoperator valued Fourier transform, and so it's fairly complicated. So FTs of the following type: 0 to infinity, g k m p q of tau, e I omega tau d tau, where omega would depend on the details of whatever this expands into after we've done all the mathematics. Well, but we now know what these g's are. They are decaying exponentials. So why don't we calculate a Fourier transform of a decaying exponential and see what it equals to. By the way, this is known as j omega. I'll talk about it in a bit more detail in a second. So, an integral from 0 to infinity, e minus tau over tau c, e I omega tau d tau. Well, we just join together the indices, so that's integral from 0 to infinity, e I omega minus 1 over tau c tau d tau. That's 1 over that, so 1 over I omega minus 1 over tau c, e I omega minus 1 over tau c tau from 0 to infinity. The infinite limit of this is 0 because we've got a decaying exponential in here. The 0 limit is equal to 1, and so what we got after we've done that is 1 over tau c minus I omega in the denominator. It's often not a good idea to drag these things with complex numbers in the denominator, so why don't we multiply and divide it by its complex conjugate? So what we'll get is 1 over tau c plus I omega, and then 1 over tau c squared minus, or plus in this case, omega squared, and multiply it also yet again on both numerator and denominator by tau c squared. That will make it tau c plus I omega tau c squared, 1 plus omega squared tau c squared. And let's separate the real and the imaginary part. The real part would be this,
1 plus omega squared tau c squared, and the imaginary part plus I omega tau c squared, 1 plus omega squared tau c squared. Now, the real part of this is a Lorentzian function with respect to omega, and this is where all those Lorentzian curves that you've probably seen already in relaxation theory are coming from. And this imaginary part is fairly small. Typically, these omegas are in the range of gigahertz, so the frequencies that we commonly encounter as part of H0. And these correlation times are in the order of nanoseconds. So gigahertz times a nanosecond equals 1, but there's an extra nanosecond here. So we've got an order of 1 in the denominator, so it's a tiny number really. And it's often insignificant compared to the real part, and so it's just commonly ignored. So what people usually stick with is just the real part of it. Now, the Fourier transform or a correlation function, commonly it's denoted J, so there'll also be K, Km, Q in this case, is known as the spectral density. And its physical meaning is the energy density of our noise as the function of the frequency. So if the noise happens to have a lot of energy on our transition frequencies, it will relax it extremely efficiently. If it doesn't, then it wouldn't. But here is the sort of expression that gives us the dependence of that power density on both the frequency and the rotational correlation time of the system. And it is these expressions that go into all of the actual expressions that you'll see during the workshop in Warwick, when we actually go to the applications in relaxation theory as parts of, for example, the Overhauser effect, magnetization transfer rate. So this is called the spectral density. That's it so far as rigid molecules go. We've looked at isotropic rotational diffusion, axial and rhombic rotational diffusion, and really for all practical purposes, if the molecule is rigid, that's about it. Nothing else is required. The unfortunate reality, however, is molecules aren't actually rigid. And there's often a situation, particularly in proteins, where we've got something fairly big that tumbles slowly with some overall rotational correlation time. But then there's something dangling from the side of it, like a side chain of amino acid, which tumbles a lot faster. Thankfully, such nested problems, which would have been absolutely formidable if we were to do them in the way that we've just done, from the ground up, thankfully they can be partitioned into individual sub-problems by making one fairly plausible assumption. We can always say that this motion, the local motion, is not correlated with the global motion of the molecule. In other words, the dynamics of this dangling tail doesn't particularly depend on which way the molecule is oriented overall. Clearly a fairly plausible assumption in many cases. And what that means is all those averages that we had in the derivations of the correlation functions for joint motions would split into products of averages for individual motions. And so the total correlation function G tau would then become a product of G global of tau, for which we can make, for example, an axial or rhombic rotational diffusion approximation, and then G local tau, which we can also try and approximate somehow. And so things become considerably easier as a result. So there is no correlation terms between these motions, and so the correlation function partitions like this. One of the most popular formalisms to handle this case assumes that this motion is restricted to a cone. And the parameter that gives us the fraction of the total area of this cone compared to the full body angle is called S squared, the order parameter. If S squared is equal to 1, there's a perfect order, and
there's no motion in here, the thing just tumbles with the overall molecular correlation time. And when s squared is equal to 0, then there's absolutely no restriction on this motion, and so it tumbles the whole way the way it likes. And everything in the middle, known in the trade as the Liparis-Tsava restricted local motion model, with the correlation time which is partitioned into what we already derived for the isotropic rotational diffusion, and a fairly similar term for the diffusion in a cone, which is derived separately, and then they're multiplied together and Fourier transformed to get the total spectral density. And the total spectral density is just an interpolation between a situation where the molecule tumbles as a whole and this thing is held rigidly, and a situation where this thing just tumbles with a complete freedom and doesn't particularly care about the rest of the molecule. So J omega is s squared tau c over 1 plus omega squared tau c squared plus 1 minus s squared, so linear interpolant between two situations, tau 1 plus omega squared tau squared, where tau is defined as 1 over tau c, so plus 1 over tau int minus 1. So this is the global correlation time. This is the internal correlation time. And that's the effective correlation time, which is this kind of average that goes into the Liparis-Tsava spectral density. This is quite useful because on the one hand it's a fairly simple model, and it can be shown that a large number of various assumptions as to the nature of the motion here all reduce ultimately to the same mathematical notation here. And on the other, it is surprisingly useful in that this order parameter gives the degree of rigidity of the local protein structure, and for that reason it's used quite a lot in protein biology, because low order parameters would mean that the loop is mobile and is unstructured. High order parameters are fairly typical of protein cores, and a massive change in an order parameter, for example, when the ligand binds, might be interpreted as a protein structure becoming more rigid to accommodate the ligand becoming more structured. So biologists find it useful. They also find useful these internal correlation times in situations where they can be extracted, because they also provide a measure of the rate of motion in various parts of the thing. Okay, so from here it is textbooks. When you look into protein NMR textbooks, you'll see quite a lot of this and how to extract these order parameters and correlation times. The last thing that I will briefly mention is that although the theory of rotational diffusion, including in these nested cases, is fairly well developed, the case of translational diffusion, that is where molecules are not just tumbling individually but also move relative to one another, and so there's an element of translational diffusion as well as rotational diffusion. Those cases are unfortunately not as simple at the end of them. You see, mathematics here was complicated when we did it, but the result was okay. In the case of translational diffusion, well, unfortunately it isn't okay. I've given you a few leads in the handout. It's basically the same mathematics with the same probability density kind of argument, except we've got to handle the full x, y, z rather than the alpha, beta, gamma. And there are various boundary conditions at the distances of closest approach. They've got to bounce directly off one another. And so various technicalities which can be solved, but unfortunately in most cases just numerically. There are no neat solutions of the kind that we have seen for the rotational case. Okay, that's the end of the lecture, and I'll see you next Monday.